Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Imagine a creature with the wingspan of a small jet plane, 33 feet, tip to tip. Yet constructed mostly of skin, tendon, and exceptionally light, hollow bone. This was Quetzalcoatlus northropi *, the largest flying animal ever known. For decades, the sheer scale of these giant pterosaurs posed a colossal engineering paradox. How did these massive, membranous wings avoid catastrophic failure? Modern aerospace engineers understand that large, thin wings are highly susceptible to something called flutter, a violent, self-exciting oscillation that can rip metal right off a plane. Yet, pterosaurs mastered the air for millions of years. Their secret wasn't rigidity, but controlled, deliberate flexibility, the aero-elastic solution. In the world of aeronautics, aero-elasticity describes the interaction of aerodynamic forces, inertial forces, and elastic forces. For a traditional aircraft, the goal is often to minimize elasticity, making the wings stiff and predictable. Any significant bending under load is seen as a vulnerability. But for the giant pterosaurs, elasticity was not a flaw, it was a fundamental part of the flight plan. Researchers, studying incredibly preserved fossils and employing advanced computational fluid dynamics (CFD) models, realized that the pterosaur wing wasn't a single, uniform surface. It was a dynamically controlled system, primarily consisting of the asterisk patagium, the thin skin membrane stretched between the elongated fourth finger and the body. This patagium was heavily reinforced with densely packed, fine fibers, known as actinofibrils. These actinofibrils weren't just structural support, they were tailored fibers that varied in thickness and orientation across the wing surface. This gradient structure meant the wing had varying stiffness, allowing different sections to react differently to turbulent air and changing speeds. This is passive morphing in action. When an air current hit a stiff, modern wing, the whole structure felt the shock. When that same current hit the pterosaur wing, the membrane would locally deform, absorbing the energy and smoothing out the flow, essentially acting as an aerodynamic shock absorber. The most critical component in this aero-elastic miracle was a structure unique to pterosaurs, the pteroid bone. This small, specialized bone articulated near the wrist, pointing forward towards the leading edge of the wing. It served as a sophisticated tensioning device. Muscles attached to the pteroid allowed the pterosaur to adjust the tension of the inner membrane, manipulating the leading edge flap, the main lift-generating surface, with immense precision. Think of the pteroid as an adjustable spoiler or slat, capable of modifying the wing's camber and sweep instantly. When a large, flexible wing encounters high speeds or unexpected gusts, the wingtip often twists downwards, reducing lift precisely when it is needed most. This is the recipe for a stall. The pterosaur's aero-elastic design countered this. Instead of fighting the pressure, the wing used its designed flexibility to distribute the load. The fibers within the patagium would stretch just enough to allow the wing to twist slightly, maintaining favorable aerodynamic shape even under high stress. It was a constantly optimizing wing profile. Furthermore, this flexibility was crucial for reducing induced drag, the drag created by generating lift. By allowing the wingtips to slightly deflect, the pterosaur could minimize the formation of powerful, turbulent wingtip vortices, leading to significantly more efficient long-distance gliding. For a massive animal that needed to cover hundreds of miles searching for food with minimal energy expenditure, this efficiency was paramount. Calculations suggest that Quetzalcoatlus may have been a powered flyer only during takeoff, spending the majority of its life exploiting thermal currents and gliding with unparalleled efficiency, thanks entirely to this dynamic, flexible structure. This ancient biological architecture has profound implications for modern design. Engineers are now actively studying biological flexibility, from birds to bats and pterosaurs, to design aero-elastic wings for drones and next-generation aircraft. Instead of heavy motors and complex hydraulic systems forcing a wing to change shape, the wing materials themselves are designed to passively respond to air pressure, leading to lighter, more fuel-efficient, and far safer flight systems. The greatest secret of flight wasn't stiffness, it was the ability to bend without breaking. For more incredible facts like this, don't forget to subscribe and turn on notifications.